Thanks for bringing up the subject of recording, Tane, because I'd forgotten to start the recording. So at least.
Okay.
Okay. Yeah. I mean, don't worry about it getting deleted from YouTube. At least for the duration of your course, it will not happen. That channel will always be there. And
So
plus,
the
the master.
11th, it will not happen, no? Till we are in 11th.
No, it will not happen for both the years. Don't worry. Like till you clear JEE, okay, you will have access to the recordings.
Yes, I was asking just because, like, in case if you want to refer to something, so we can, no?
Yeah. You can. You'll have that access to the recording throughout, like till the exam.
Okay, sir.
Done.
Yeah. Okay. Let's move on to fifth question. Okay. So the first few questions, unfortunately, I've missed out the recording, but you'll have the notes. So just refer to it. If there's any doubt later, you can discuss with me. So fifth question of this, it's saying that sand is poured onto a pipe, from a pipe rather, and it forms a cone on the ground such that, okay, in such a way that the height of the cone is always 1/6 the radius of the base. So you realize that it's a very flattish kind of cone because the height is very small compared to the radius of the base. So typically it's some kind of shape like this. So what is the formula of volume of cone? People remember?
So 1/3 pi r square.
Yes, pi r square into vertical height, right? So that is the formula we'll be using here. Only now there is additionally a relationship between the vertical height and the radius. So even though the cone is expanding, but always at any instant the height is 1/6 the radius. So the volume, which is 1/3 pi r square h, is becoming how much? 1/18 pi r cube. Right? This is the same thing you had used in the question. So now as sand is falling from top like this, it is falling at a rate which is given to us. So gradually this is increasing in size, but it's increasing proportionately. That always h increases by a factor which is 1/6 of the rate of change of r. So the volume rate, so we'll write that as dv by dt. That is given to us as, how much is it now? 12 centimeter cube, 12 cc per second. So we have to find the rate of increase of height of the cone. So we have to find dh by dt at an instant when the height is equal to 4 centimeters. Okay. So since we want to find dh by dt, let's actually reverse this. Let's write it like this, that r is equal to 6h. So volume, which is 1/3 pi r square h, is 1/3 pi into, so that we get it in terms of h. Okay. So this will become 12 pi h cube, because we want to find dh by dt. Now use chain rule. So dv by dt is equal to rate of change of 12 pi h cube. Okay. So that is equal to d by dh. Remember, h is a variable here. So into dh by dt. So this is our relationship. Now it's like a bit of a reverse problem, that question is giving us the value of dv by dt and we have to calculate the value of dh by dt. So this value is given to us as, but before that, let's solve this. So dv by dt will become 36 pi h square, right, into dh by dt. So let's invert this now. Dh by dt is dv by dt divided by 36 pi h square. Now substitute the information. Okay, so the rate at which the height is changing will become dv by dt, which is 12 cubic centimeters per second, divided by 36 pi into 4 centimeter square. So that is going to give us how much now? 1 by 48 pi. And the unit will be in centimeters per second because it's cubic centimeters per second divided by centimeter square. Is the question clear now?
So,
Yes,
Yeah.
I got it. Yes.
Okay.
so how did you get that 36 pi h square?
इसको differentiate किया ना 12 pi h cube को
Acha,
d by
okay.
dh है ना, that 12
Okay.
pi is a constant, so just h cube's differentiation 3h square.
Yes, sir, got it.
Uh, you can send it on WhatsApp also to me right now if you have a question which is.
Okay, sir. I sent you.
Can you send it on WhatsApp? Any other doubt from exercise 3? Or should I move on to exercise 2 doubts?
Ninth one.
9th one, okay. And Avi, these questions you have sent are for exercise 3 or exercise 2? Okay, okay, I got it. So let's look at question number 9. This is also a very interesting question. We'll solve it 2 methods. One is calculus and one is using trigonometry. So in the calculus method, it's a little bit like that problem we did using Pythagoras theorem earlier. That that ladder which was slipping, that one. So just inscribe a rectangle inside the circle and take like the length of the rectangle to be x and the width to be y. So you'll see there's a relation between x, y and the diameter of this thing and the diameter of the circle.
Diagonal.
Okay. Yeah, that diagonal will become the diameter of the circle. So 2r. Now you express the area in terms of x, y, and then express y in terms of x. So you'll get the area as a function of x. So then you can use maximum minimum to get the maximum area. And you will see that the area is maximum when you have the result that x is equal to y, or x is in fact equal to, it will be like a chord that is subtending 90 degrees. So it will be r root 2. Okay, I mean, I'll take that question after we finish this. Yeah, I got it. It's that cylinder wala question. It's like, yeah, this is a bit of a tricky question, but once I explain how to set up the question, you'll see the solving is easy. It's just like how to set the question up for maximum minimum. Okay, let's come to 9th question. Again, exercise 3 only. So let's say this is the circle we are talking about and it's of radius r. Now we are free to inscribe any type of rectangle within the circle. That means we can take a rectangle which looks like this. If we want, alternately, we can take a rectangle that looks like this. If we want, we are free to select any rectangle as long as it's inscribed. But we have to see in what condition the rectangle that we have chosen has the maximum area. So let's take in general this to be x and y. Okay. So the hypotenuse of this right angle triangle formed by x and y, or you can say the diagonal of the rectangle, is nothing but the diameter of the circle. So this will be 2r. We have the relation that x square plus y square is equal to 4r square, 2r whole square. Okay. So y is again square root of 4r square minus x square. So now the area of this rectangle, this area, it is x into y. So the area is equal to x into square root of 4r square minus x square. Okay. Now again, this looks like a very scary function, and if you try and differentiate it, it is going to be very lengthy. But we can use a trick here, okay? And that trick is like this: that if you look at the square of the area, that's something very simple. It is x square into 4r square minus x square. So if area is maximum, then area square will also be maximum. Okay. So now we just want to do one thing. We want to find the condition for a square, instead of this, for a square to be maximum. Okay. So think of a square as a function of x, and as a function of x, it is 4r square x square minus x to the power 4. So think of this and find the maximum of this function. And once we got the maximum of this function, we know that the maximum of the area will be square root of this function's maximum value. You following so far now? Okay. So this is one approach to the problem, and you can do it quite easily using maximum minima concept that we discussed. So just try it out from here. We'll discuss. Yes. Okay. So not only that, now you're getting the condition for the function to be maxima, na, that x is that much. So that is a condition for it to become a square, you will see, because y will become equal to x. So that proves the question what it was asking. So derivative of the function is this. Okay. So that is 8r square x minus 4x cube. So we can take 4x 8r square minus x square common. So 4x into 2 root 2r minus x into 2 root 2r plus x. So this is the derivative. Okay. So second derivative is 8r square minus 12x square. Now here you can see one more thing, that this function logically has a limit on the value of x. X has to be greater than 0, otherwise we don't have a square, and it cannot be less than, it cannot be equal to 2r, because again then we just have a line. So there is a restricted domain for the function, okay, or restricted set of values of. So now you can see that for maxima,
So,
f prime x should be 0. Yes.
so there you wrote 8r square minus x square while taking 4x common.
Huh?
It should be like
Oh,
a
sorry.
multi.
Yeah, my mistake. It should be 2 now. Yeah. So this will just be root 2. Yes. I took 4 common. Okay. So this is 4x into root 2r minus x into root 2r plus x. So derivative is 0 for x equal to 0, x equal to root 2r, x equal to minus root 2r. But you can see that out of these two are not allowed only, because x cannot be negative, x can't be 0. X can only be a value which is something between 0 and root 2r. So anyway, we know this, and we can see that second derivative at this value will become how much? It will be 8r square minus 12 into x square. So that is root 2r whole square. So you can see it's a negative quantity. So it's fulfilling the condition for maxima. So you can see that this function has a maxima at x equal to root 2r. So that means the area, which is square root of this function, is also maximum for x equal to root 2r. So now you can see that the maximum value of that area will be this when x is equal to root 2r. So when x is equal to root 2r, it's very easy to understand that it's a square. So the maximum area will become 2r square for square x equal to y equal to 2. Okay, so this is the proper calculus way of solving the question, how you are supposed to do it here. But however, this question also interestingly has a shortcut method, which is nothing to do with calculus at all, but to do with your knowledge in trigonometry. We'll see using that also. Vedant, we got that bit up by the relationship between x and y. See, x square plus y square is 4r square. So when x is root 2r, we get this. Yeah, scroll up. Okay, so this is clear now.
Yes.
Okay. Now the trigonometry method I was telling you, you will see that's pretty fast actually. There's a different approach altogether to this question. So if you just express the sides of the rectangle in terms of an angle instead of expressing it as x and y, so immediately you see this simple relationship here. If this angle is some theta, then you can see what we had taken as x would become 2r cos theta, and what we had taken as y would become 2r sin theta. Yeah. So our area, which is x into y, becomes 4r square sin theta cos theta. Now this is where your trigonometry comes in. This can be expressed as 2r square into sin 2 theta. Okay. In this you can see that since x has to be greater than 0 and less than 2r, therefore basically my theta has to be greater than 0 and less than pi by 2. So from this you can see that the maximum value of area is equal to 2r square, because sin 2 theta's maximum possible value is 1, and that occurs for 2 theta equal to pi by 2. That means theta equal to pi by 4 or 45 degrees. And in this condition, therefore, for A to be maximum, theta should be equal to pi by 4. So x should be r root 2. Should be a square. So this is a very clever one-line solution, but as you can see, this is taking advantage of trigonometry and an identity in trigonometry that 2 sin theta cos theta is sin 2 theta. That's the first identity, and then making use of this fact. Okay, next I will take up one of the questions from your major test, then I'll go back to exercise 2 because that's also kind of related to maxima minima. So I just want to. So you'll remember when I put up the question, is that integer answer type question from MT, where to begin with we had a rod which had a negligible thickness, okay, but an initial length of 12 centimeters. Now this rod was expanding into a cylinder such that if this was the situation at t equal to 0, then after some time it had become a cylinder whose radius is expanding with time, but whose length is compressing. So as the rod is changing shape, it is kind of morphing into a cylinder of larger and larger radius, but also lesser and lesser length. The shape is of the cylinder is going more and more towards a disk. Eventually, its length will compress to 0. Okay, so at some time t, the length has become L, which is less than L0, and the radius has become R. So L, it was given to us that the rate at which the length is changing is that it's decreasing at the rate of the length is decreasing uniformly at the rate of alpha. So write it as minus 4 meters per minute. Alpha is 4 meters per minute, but is the rate at which the length is decreasing. Okay. At this uniform rate. So we can say L is equal to initial length minus alpha t, where alpha is equal to this quantity, 4 meters per minute. Whereas the radius was expanding such that it's expanding at the uniform rate of beta, which is further given to us as 0.5 meters per minute. So now initial radius was 0. Here R0 is tending to 0 at t equal to 0. So radius as a function of time will just become beta t. So this is the length as a function of time. This is the radius as a function of time. Now we have to find the time at which the volume is maximum. Find the value of the instantaneous time at which the volume of the cylinder is maximum. So first of all, express the volume as a function of time. So pi r square L. So this becomes pi beta t whole square into L0 minus alpha t. So as you can see, this is my volume as a function of time. Now use maximum minimum. Use the concept of maximum minimum from calculus to find the time at which the volume is maximum. Okay, just try this out.
We only have to find maxima or both maximum and minimum.
In the question, actually, you have to find the time, the value of time at which the volume is maximum.
Okay.
Got it? Huh?
Sir.
That time will come out to be an integer value in minutes. It was an integer answer type question.
It's 0.5 meter, right? Beta value.
Meters per minute. Okay, it's changing with respect to time. No?
Yes, sir, but it's 0.5 meter per minute.
Yeah, it's half a meter per minute. So the radius is increasing by half meters every minute, whereas the length is decreasing by 4 meters per minute. Oh, it should be in centimeters, no? Because the length was in centimeters. Okay, just let me check the question. Actually, just change the length in meters. Change it to 12 meters. Okay. Because you can't have something in centimeters and its length is decreasing at few meters per minute. So just change the initial length to 12 meters instead of 12 centimeters. Okay, so let's look at this. So as you can see, this volume is basically a cubic function of time. So you can take this pi beta square outside, okay, and it is L naught t square minus alpha t cube. So yeah, so dv by dt is pi b square into differentiation of this term. So 2 L naught t minus 3 alpha t square, and second derivative is similarly 2 L naught minus 6 alpha t like this. Okay. Now the condition for maxima, dv by dt should be 0 and second derivative should be negative. So dv by dt is 0 means 2 L naught t minus 3 alpha t square should be 0. So either t is 0, which is obviously not the case because initially the volume was 0 now. So we get two solutions for this. One is t equal to 0, but that's not the case because at t equal to 0, you can see the volume was 0. So it's actually minimum. Okay, whereas at the other one, t equal to 2L naught by 3 alpha. This is the one which will give us the maximum condition. You can check it by putting it in the second derivative also. If you put this value of time in the second derivative, you will see that you will get a negative quantity. So the second derivative is 2L naught minus 6 alpha into this will become how much? It will become 4L naught. Okay, so it will be
Yes.
negative. So it's, you can also check it out that it's given. But as I said, you don't even need to check because you can already see t equal to 0 has got ruled out. So only one option left. Okay? Because this is the initial, and initially you know that the volume was 0. So it can't be maximum. Okay? So the maximum must be happening at this point. So our answer is now this only. Okay. But obviously in this we have to substitute. So 2 into 12, I'll make this meters because, and alpha was how much now? It was 4 meters per minute or something. Yeah, alpha's value was 4 meters per minute. So we'll get the answer in minutes. So we'll get it as 2 minutes. That should be the answer. This is the time when volume is maximum. So logically, you'll also understand what is happening to this body is now. As time is progressing, its radius is increasing, but also its this thing, its length is compressing. So what you'll see is that, see, the initial length was 12 meters, okay, and alpha was 4 meters per minute. So L naught minus alpha t, after a matter of 3 minutes, okay, the volume has become 0 actually because L has become 0. So you can see that L becomes 0 at t equal to 3 minutes. So that is when the volume again becomes 0. Whereas radius was 0 at t equal to 0. So again, volume was 0 at that time. So now you can visualize that the volume, how it's changing with time. It's starting from 0 because the thickness was negligible. It reaches some maxima and then again it compresses to 0 at what time? At 3 minutes. Because now it's become a disc instead of a cylinder. The length has compressed to 0. So in between, there must be some time when the volume has reached a maximum value. So that time we are calculating here, this has come out to be 2 minutes. The answer has come out to be 2 minutes. Okay, so hope this is clear, people.
Yes, sir.
Okay, very good. So as I said, the solving was easy. The difficult thing in this question was to figure out how you'll express the function and all that. Okay, now let's finally come to exercise 2 doubts. Okay. So Avi, you have sent me some doubts and so far nobody else has sent doubts. So I'll start with yours. Question number 4 of exercise 2.
Yes.
The Yeah, turn to your module 1, page number 39, exercise 2, question number 4. We have to find the derivative of sine of x cube. Okay, so it's a composite function. Now, the only thing that in this question you should not get confused between sine cube x and sine of x cube. When the cube is written above the x, it means sine of x cube. It doesn't mean sine cube x. Whereas if the 3 was written above sine, in between the sine and x, then it is sine cube x. That means sine x is whole cube. Okay, this point is clear now?
Yes.
The difference between sine x cube and sine cube x. Okay, this is actually the more proper way of writing this would be this. Okay, whereas this is actually sine x whole thing to the power 3. So for example, sine of, let's say, pi by 6, sine cube pi by 6 would be sine pi by 6 to the power 3. So that's half to the power 3. So that would be 1 by 8. Okay, but sine of, for example, this would be a little odd anyway, but suppose we have pi by 4 cube. So this is sine of pi cube by 64, and pi square is nearly 10. So it's like sine of 10 pi by 64, sine pi by 6.4. So whatever you convert it to degrees. So that's the difference between the two. So now in this question, exercise 2, module question number 4, we have the function y is equal to sine x cube, and we have to find dy by dx. So I'll show you both by the shortcut method as well as the proper substitution method for chain rule. So chain rule by substitution method. So when you look at the function, you realize that, to given some value of x, how to get the value of y? First, I have to cube that x, and then I have to operate sine on it. Understood that point now, Abhi?
Yes, sir.
So मैं पहले cube करूँगा, then I'll get x cube, and then I'll find sine of that. So that will give me y is equal to sine of x cube. So I should take my inside function as what? X cube. So I should substitute x cube as the dummy variable, gx or z. Okay, so y becomes sine of z, that is f of gx, that kind of. Okay, so now making use of this, now we come to the chain rule step, that dy by dx is dy by dz into dz by dx. Now substitute this here, so dy by dz will become what? Cos z, and substitute this z equal to x cube here. So this will become what? Differentiation of x cube,
3x square.
3x square.
and then resubstitute. So dy by dx is becoming what? 3x square into cos of x cube. Okay, this should be the answer. So this is the full descriptive way of solving the question with all the steps and all that. We can cut down some of the steps and do it faster also at the exam level, but that is provided you have enough practice and you have the confidence that you won't make mistakes while skipping steps. Otherwise, if you want to do it systematically, then this is the proper way of solving it. Right? Now the other method is the shortcut one, that given if y is f of gx, then directly what is dy by dx? It is derivative of f on gx, okay, f prime of gx into derivative of g. So in this function y is equal to sine of x cube, we can already see that gx is x cube and f of gx is sine of gx. So f's derivative is what? Cos. So dy by dx will become cos of gx, and gx is what? X cube into g prime x, which is 3x square. So directly it is 3x square. So directly it is 3x square cos x cube. Have you understood how I have written this directly here, Abhi?
Yes, sir.
Okay, so like eventually your goal is to be able to do this directly without making a mistake. But at the same time, like while you're getting the confidence in these type of questions, you can always start by the step-by-step substitution chain rule method. Okay, so make a note of this if required. And next, we are coming to question number 8 in the same page, on the same page rather. Okay. So that's another chain rule question, e raised power square root of 2x. Now try it out by the direct method if possible.
Sure.
Okay, so people have tried out question number 8. The square root of 2x. Yeah. So you want to find out dy by dx. So again, this is f of gx, where gx is what it is, square root of 2x. Okay. So g prime x is root 2 comes outside and 1 by 2 root x. So it's 1 upon root x. And f of gx is e raised power gx. Now we know that derivative of exponential function is the function itself. So f prime of gx will be e raised by gx only. That's what makes this kind of thing easier. Okay. So if I use that method, dy by dx is exponential of the same function into derivative of that function, which is just now we saw 1 by root x. So e raised by square root of 2x divided by root x.
But 2 root x, right? Root 2x.
So there you
1 by
multiply
root
it
2x.
by 1. So it will be root 2. Like root 2 into root 2 is 2, sir. So root
Oh, sorry,
2.
sorry. Yeah. Root 2 by 2 will give you another root 2 in the denominator, right? So this will be square root of 2x, right?
Yeah.
So any exponential thing you should be able to solve directly, because you know if you have y is equal to e raised power any function, directly it becomes dy by dx becomes same function e raised power gx but into derivative of gx. So for example, if you have y is equal to e raised power sine x, you can see directly that dy by dx will be e raised power sine x into derivative of sine x, which is cos x. That's it. It should be simple like this. Okay. And of course, you can always go with the substitution method. You can substitute root 2x as z. So y becomes e raised power z, and then use. So see that this becomes e raised power z into 1 by root 2x. Okay, so that's all right. So that's the 8th question. Next, we are looking at, is it question number 10? Okay. Yeah, 10 is like a very sort of lengthy version of product rule. Okay. So I can understand why this question might have created some problem. But if you just understand that we have to apply product rule twice because it's the product of 3 things. So it's like, let's say A into B into C. So you take any 2 in a bracket, like A into B, take it in a bracket into C and apply product rule and then open the bracket when you differentiate once more. So product rule will apply twice. What I'm basically saying is that if y is the product of 3 functions, let's say f, g and h. So dy by dx, now just treat it like I'm taking f separately and g into h as one bracket. So it become f prime, okay, into gh plus f into derivative of gh, and then open this once more. So it becomes f prime gh plus f into g prime h plus gh prime. Interestingly, you'll see it becomes like this. It becomes f prime gh plus f g prime h plus f g h prime. It becomes like a permutation or a combination of the 3 terms added up, where in each term one of them is differentiated and the other 2 are just multiplied. So this is the type of concept you'll use in 10th. I'll just put up the question in a moment. Okay, so let's put up this question and see how we can apply this. So you don't need to memorize that as a separate formula, like product rule for three functions, f prime into gx plus f into g prime, like that. You don't need to memorize. You just need to remember this concept that we'll just treat it like this, that let's say take it as x square into this bracket, which is the product of these two terms. So now treat this like your first function and this whole bracket as your second function and use product rule. So it is differentiation of the first function multiplied by the second function plus first function into differentiation of the second. And then when it comes to differentiation of the second, again apply product rule. So this is 2x into sine x ln x plus x square into, now when you take this inside, again it becomes differentiation of sine x into ln x plus sine x into differentiation of ln x. So 2x sine x ln x. I'm taking the x square inside, x square cos x ln x plus x square into sine x into 1 by x. So that will just become x sine x, because this term will become 1 by x. Okay, so hope this is also clear.
So,
Yes,
so can you tell once more how did you got x sin x?
x sin x, because देखो ये term पे बाहर x square है ना, like let me just solve this bracket first, then it will become clear. Got it, na? Okay, so this is cos x into ln x plus sin x into 1 by x, and now you just take the x square inside.
Yeah, so x and x get cancelled, so it becomes x sin x.
Yeah. Okay, so that's the 10th question. Let's move on. I think we have just a couple of questions left now. What is it? 14th question. Yeah, yeah. Okay, right now it's fine. After this, we'll be doing the 14th question. Just putting it up on the board. So y is equal to 1 upon square root of 2x plus 1. You want to find dy by dx. So this is again composite function, chain rule you'll have to use. Okay, so this 14th question, what should we take as our f of gx and what is our gx? Yes, very good, Rishikesh, that's correct. Okay. The inside function is 2x plus 1. No? So 2x plus 1 is our gx. Okay. And 1 upon square root of 2x plus 1 is basically, which is our f of gx. So f is the function, like let's say fz is 1 by root z. So derivative of this is how much? Minus 1 by 2 z to the power minus 3 by 2 or minus 1 by 2 z to the power 3 by 2. Okay. So now so if f prime of z is this, then f prime of gx is how much? Minus 1 by 2 into gx, which is 2x plus 1 to the power 3 by 2 into g prime x. Now g prime x is very easy, it's directly 2. So it becomes minus 1 upon 2x plus 1 to the power 3 by 2. Okay, so this is probably the shortest way in which you can do the question without doing the full substitution and all that. Okay, any other question from exercise 2 pending, please let me know, because we will now be in a situation where we'll be concentrating more and more fully on kinematics in future for the next few weeks. Of course, kinematics itself will involve some applications of calculus, but okay, so then I'm assuming that doubts in calculus are all solved, right?
Yes, sir.
Okay, very good. So we will move on a little bit in kinematics in 1D or motion along a straight line, what we were discussing in the last lecture. I think somebody here also sent me a message that how many lectures of kinematics have happened. Now, I will not be considering the board lecture that we had. I think most of you were present, right, in that one board lecture for kinematics.
Yes, sir.
That is not a part of this series of lectures. Okay, this is kinematics from the basics. So we have had just the one lecture of kinematics so far. Okay, in which also we had basically started with some doubts of calculus, and then we moved on to kinematics. So we had started with motion along a straight line. So I'll quickly recap the definitions, and then we'll move on to the important special case of uniformly accelerated motion.
So,
Yes, yes, Beta.
so can you once again just also tell like what is the integration of ln x?
Integration of ln x, Beta, is a very complicated thing. So that is why we'll avoid it for the moment. Integration of ln x is done by something called integration by parts.
Okay.
Which is a sort of adaptation of product rule in integration. So what we do to integrate ln x is we treat it as the product of 1 into ln x. Okay, and there is then something called integration by parts, where if you have the product of two functions f and g, then you can integrate it by using a sort of a formula. So that is why we will avoid it at the moment. You will learn about this in advanced calculus in maths in 12th.
Okay, sir.
Okay. In 12th class maths, you will learn about this. So the main thing is, one of the reasons it's not that we can't do it, but this is not required in physics, and we just have to learn a whole different method of integration, which is not going to serve us any purpose right now. So it's not part of the basic calculus syllabus, but it will be in your 12th. So you need not worry about this at the moment at all. Okay, now just keeping this aside. So we had started with motion along a straight line. And in that we had started by understanding that suppose that straight line is the x-axis. Then the position at any instant, the instantaneous position is designated by the coordinate. Okay, so the displacement in any interval of time becomes the change in the x coordinate, or it becomes the final x coordinate minus the initial x coordinate. Okay. So velocity then accordingly is defined as instantaneous velocity is rate of change of position or rate of change of displacement. They are one and the same thing. And average velocity is average rate of change of position, which is basically x2 minus x1 upon t2 minus t1, or x2 minus x1 is nothing but the displacement. So it is the total displacement upon total time. And then we saw that acceleration again is defined as instantaneous acceleration being dv by dt and average acceleration being delta v by delta. So all these definitions we had seen, and then we had seen the reverse of these definitions, that we had seen displacement is integration of velocity with respect to time, and change in velocity is integration of acceleration with respect to time. So these were some of the important things we had seen in the last lecture, including a couple of applications. Now today we will start with an important special case of this, which is the motion when the acceleration is uniform. Okay. But before that, we will look at one more relationship, one more set of relationships between acceleration and other parameters. So you don't need to note this down because this is just a recap of last lecture. Now the additional thing that we'll start with today is that acceleration is dv by dt. Okay. So if we apply chain rule, by application of chain rule, you can also see that acceleration can be expressed as dv by ds into ds by dt. This is our chain rule step. That dv by dt is dv by ds into ds by dt. And since ds by dt is nothing but the instantaneous velocity, so the acceleration can also be defined as v dv by ds. Okay, so this is an alternate relation that is of acceleration in terms of velocity and displacement instead of in terms of velocity and time. Yeah, double derivative is also there, but that is a slightly different thing, Vansh. Okay. Here I'm talking about the relationship between v and s. I mean acceleration in terms of the relationship between v and s. Okay. We have this also, of course, that E is dv by dt and v in turn is ds by dt. So this is also true. Okay. And we'll come to this relation also. But right now I'm focusing on this, okay, for the moment. Okay. Okay, so suppose, so let's see a quick application of this. So suppose we have an example where a 1D motion is such that velocity varies with displacement as v equal to, let's say, 2 root s, where s is in meters and v is in meters per second. So now from this we want to do two things. One is, over, too small, wait. Okay, just make a note of this, then I'll finish the question. Note down this part first, this relationship above.
So done.
Sorry, beta, what was the doubt?
So done.
So just a second.
Yeah, okay. Yeah, I mean, just finish writing and then try out this question, So now with this, what we want to do is we want to find, first of all, acceleration as a function of the displacement S. Okay. And from that, we want to find acceleration at an instant when V is equal to 1 meter per second. And another thing we'll do here is we will also find displacement S as a function of time, which is not related to what I just told you above. That's something else altogether. But we'll see that can also be done from the basic definitions here. Yes, very good. That's correct. Okay. So here you'll see that V is equal to 2 root S. So that implies that acceleration, which is V dV by ds. Very interestingly, when you do this calculation, you get this now. So it come out to be 2. It's a uniform acceleration, interestingly. Yeah. So obviously, because it happens to be a uniform acceleration, so A is equal to 2 meters per second square when the velocity is 1 meter per second, and all other times. Not just that instant, but at all other times. Okay. Now to answer the third part, what we have to do is, see, V is given as a function of S. No? So V can be written as ds by dt. So that is, so we'll cross multiply this and integrate this like this one. So just try it out by this method, we'll discuss. Of course, you can use the equations of motion with uniform acceleration also, but
Sir, we could directly use this one, right? A is equal to d2s by dt square.
yes, we could do that also. But then the problem is that in that, when you have to put the limits, there'll be a problem because you don't know the initial velocity. You are understanding my point now?
Yes, sir.
Sir,
Yeah.
sir, I didn't understand that third one. How did you calculate it?
Yeah, I haven't calculated yet, but the method I'll just show you. Okay. So the method is, see, V is given as a function of S. No? And what is
Yes,
that
sir.
function? Is 2 root S. Okay. So अभी मैं V को by definition क्या लिखूंगा? ds by dt.
Yes,
ds
sir.
by 2 root S. So now I can cross multiply this. Huh? ds upon root S is 2 dt, for example. I can just write it this way.
Yes, sir.
Now I can integrate this equation. And obviously, logically, at t equal to 0, what is the displacement? It's 0. Whereas at some
0.
time, the displacement is some value s. Okay. Now, what is the integration of 1 by root s? What is this integration? Okay. 2 root x, hota na?
Ah, sir.
So this will be 2 root s, but we'll put the limits from 0 to s. Now, on the other side, 2 is a constant, so it just comes outside. Okay, from 0 to t. So on putting the limits, the upper limit is this, the lower limit is 0, and on the other side also, lower limit is 0. So we get root s is equal to t. That means s is equal to t square. So this is the displacement as a function of time. Okay, so hope this question is clear. Now, later I'll come back to this question once with the formula-based method also, because it's uniform acceleration. Okay, but this is just to demonstrate. Now, if for example that function had been something else, like instead of v being 2 root s, which gave us constant acceleration. Suppose it was something else, like v was, let's say, 2s square, or it was let's say 2 by root s or something like this. Then we would have got a different relation. We would have got variable acceleration. But the method is the same. Whenever v is given as a function of s, we use this relation that acceleration is equal to v dv by ds. So this is a method that we use. Okay, so that is the point of this. Okay. Now let's come to the special case of uniformly accelerated motion along a straight line. So we have talked about this in the board lecture also, but we'll discuss in more detail now. 1D motion is the same thing as motion along a straight line. So acceleration, its value is equal to a, which is a constant. And at t equal to 0, the initial velocity is equal to u. Okay. So then the first thing we see that this acceleration this implies that dv by dt, which is a, is constant. Okay. So if we integrate this relation, we'd seen earlier that integration of acceleration with respect to time is change in velocity. So at t equal to 0, the initial velocity is u, and at some time t, let's say the instantaneous velocity is v. So at t equal to t, the instantaneous velocity, that means the velocity at that instant or at that moment, is v, whereas initial velocity is u, what we've seen above. So when we integrate both sides of this equation, left hand side is very simple. It will give us this from u to v. Right hand side, a will come outside. So this integration of a dt, a will come outside and this will apply. So this will be 80 from 0 to t. So this becomes v minus u is equal to 80. Or this is how we prove the first equation of uniformly accelerated motion using integral calculus, that when acceleration is constant, then velocity varies with time like this. So this is instantaneous velocity as a function of time. Okay, that's the first of the three equations. So here the integral we are using is a very simple one, that integration of dx is x plus c. So integration of dx from some constant a to b, let's say, will become x from a to b. So that will become upper limit minus lower limit. So this integral has been used in both the places, on the left hand side also, on the right hand side also.
So,
What is the doubt?
so where you wrote integration of dv, there you took v as u and u as v, right?
No, the lower limit is u and the upper limit is v. And in the integration, the variable of integration is v. Understanding the point now? So where this is concerned, this integration symbol, the v over here, this is the variable of integration. But here the u that is there, this is the lower limit, and here the v that is there on top, that is the upper limit. So basically just think of it like this integral here, but x is replaced with v, the lower limit a is replaced with the symbol u, and the upper limit b is also replaced with the symbol v.
Yes.
Okay, now from this equation we get the second one, because we know that v is ds by dt. So if ds by dt is u plus at, where of course you understand u and a are constants, because
Sir,
u
can
is
you
the,
scroll for me?
yeah, u is the value of the initial velocity and a is given to us to be constant.
Sir, you can scroll down. Thank you, sir.
Yeah, so this is done. And now next thing, see, we got this. So if we cross multiply this, we get this. Okay. Remember this u and a are constants because u is the initial velocity. So it's not a variable. Okay. And a is the uniform acceleration. So it's a constant. So at time 0, the displacement is 0. At time t, the instantaneous displacement is s. So again, on the left hand side, we have the same thing. S going from 0 to s. On the right hand side, u plus at, its integration will become ut plus half at square. And again, the limits are from 0 to t. This is just like integration of, let's say, a plus bx with respect to x. That becomes like this. Okay, so it becomes ax plus b into x square by 2 plus c. So like that, integration of u plus at will become ut plus half at square plus c as an indefinite integration. Now we are putting the limits on this. So on putting the limits, we get the second equation of motion, that is s is equal to ut plus half at square, which gives us the instantaneous displacement as a function of time. Okay, so this one is clear, na? This derivation.
Yes, sir.
And finally, we move to the third one, which is actually a very simple equation. So in the third one, we'll be using that definition of acceleration. Okay. Instantaneous acceleration in terms of dv by ds. So here v dv by ds, which is a, is a constant, because acceleration is a constant. So now if we cross multiply and integrate, we will get that third equation, that v square is equal to 2as, that one. Because initially when displacement was 0, the initial velocity is u, and at some time t when the displacement is s, the instantaneous velocity is v. So at t equal to 0, s is equal to 0 and v is equal to u, whereas at some time, instantaneous time t, when the displacement is s, the instantaneous velocity is v. So now the left hand side becomes an integral of this type, x dx, that is x square by 2 plus c. So if you do x dx from a to b, you'll get x square by 2 from a to b. So that will simply become b square minus a square by 2. So this integral will come on the left hand side. Whereas on the right hand side, again, a is constant, so it comes outside. So this becomes v square by 2 minus u square by 2 is equal to as, going from 0 to s. So v square minus u square whole divided by 2, we can write it as is as. So cross multiply, and this will give us the relation, which is the third equation of motion. And this gives us the relationship between instantaneous velocity and displacement s. So these equations are something that we'll be using to solve all problems related to uniformly accelerated 1D motion, including the motion of bodies or particles which are in free fall under gravity or which are vertically projected. We were discussing part of that in the board lecture also, but we'll be doing much more in-depth problem solving and numerical questions and all that at the JEE level. So we'll take all that from the beginning in the next lecture. Okay, people, so that's it for today's session. Thanks for attending. Wish you all the best.
Thank you, sir.
Thank you, sir.
Do we have homework today?
Yeah, I will send you some homework from the module exercise.
Okay, sir.
Kinematics is there in the same module, no? After basic calculus,
Yes,
the next
sir.
chapter.
And sir, are we supposed to solve the exercise 4 of calculus? It's the application of calculus in kinematics.
In fact, yes. In fact, that exercise has to be solved now because we have done 1D motion with the application of calculus. In today's lecture also, we solved some questions and previous lecture also. So now you can go ahead and complete that exercise 4 also.
Okay, sir.
In fact, the first thing for you in kinematics to do will be that exercise 4. Then the questions from the second chapter, the kinematics chapter. Okay.